Hello guys, today we are going to look into how to perform Booth's algorithm. Booth's algorithm is basically used to multiply two numbers, and these two numbers are in 2's complement where m and n are represented using 2's complement. Okay, so basically now we can say that Booth's algorithm is to multiply signed numbers, and the signed numbers representation is 2's complement. That you have to keep in mind. If it is 2's complement method, then that sequence counter, the value of the sequence counter needs to be determined. The common mistake what we do in performing the Booth's algorithm is that the sequence counter is not properly fixed. Now, how do we need to fix this sequence counter? You have to remember the range for the 2's complement, which is given as minus 2 raised to n minus 1 to plus 2 raised to n minus 1 minus of 1. Say for example, if I fix the sequence counter value as 3, then the range of the in 2's complement will be from minus 4 to plus 3. Substitute the value of n equal to 3 here. So 3 minus 1 is 2. 2 raised to 2 is 4. So 2 raised to 2 is 4. 4 minus 1 is 3. And similarly, when I put n equal to sequence counter as 4, the range of the number will be from minus 8 to plus 7. And similarly, when I put the value of n equal to 5, the range of the number, it starts from minus 16 to plus 15. Now remember, if I give any two numbers, multiplication of two numbers, say for example, it is minus 9 multiplied by plus 3. Okay, plus is not necessary. If it is not mentioned, you have to consider it as plus. Now, what is the sequence counter you are going to fix while performing the Booth's algorithm for this? Now look at this 9. 9, how many bits it will take? 4 bits, right? And how many bits? 3 will, to represent 3, how many bits we require? Only 2 bits, right? So how many bits we need to perform the sequence counter? How many iterations you have to perform now? Sequence counter, neither it is 4 nor it is 2, it should be 5. Why? Now look at this, minus 9, where it is available in this range. Minus 9 is available, answer is no. Minus 9 is available in this range, answer is no. Minus 9 is available in this range, answer is yes, right? So plus 3 is also a part of this range. So plus 3 needs to be also represented using 5 bits like this, and minus 9 needs to be represented using 5 bits. Now what is the procedure to represent minus 9? First you have to write plus 9. So how to write the plus 9? Using 5 bits you have to, not 4 bits. If you take 4 bits, you go wrong, right? So it is 0, 1, 0, 0, 1. So using 5 bits you have to perform. So this is plus 9, takes 1's complement, 1, 0, 1, 1, 0, and then add 1. So you are going to get finally the number that represent minus 9. So this extra care you have to take while fixing the sequence counter. Fine. Now when we do the hardware implementation for the Booth's algorithm, various registers are required. The first, which registers are required? Accumulator register is required, QR register is required, BR register is required, and then I require a flip-flop, that is QN plus 1, and I require a counter, that is sequence counter. So these are the hardware requirements. Now what is the purpose of these hardware requirements, hardware components? Sequence counter is to hold the number of iteration. Qn plus 1 is a flip-flop. to carry out the iterations. BR register is used to hold the multiplicand. QR is used to hold the multiplier, and accumulator register is used to hold the part of the resultant, right? So this is to hold the number of iterations. Qn plus 1 will represent as an flip-flop that will help us to perform the iteration. BR register is used to hold the multiplicand value. QR register is used to hold the multiplier value, and accumulator register is used to hold the resultant value. Okay, the part of the resultant, the higher part of the resultant. And QR at the last, QR also will hold the lower part of the resultant, right? Now, what is the initial step? So I will start performing the Booth's algorithm. So our algorithm will start. So you have to fix the multiplicand and multiplier. So I use BR to fix the multiplicand, and QR register, I use it to hold the multiplier value, right? And once it is done, so initialization, initially the accumulator value needs to be put zeros, a sequence of zeros. That depends upon after making accumulator, initialize the accumulator to 0, then your sequence counter, you have to fix the value of n, how many times the number of iterations. And please remember how to fix this, the value of n. Remember this formula. You have to look at the given numbers, the multiplicand and the multiplier, in which range it will fall. Both the numbers, like say for example -9, right, plus 3 will fall under n equal to 3, n equal to 4, and n equal to 5, but -9 will fall under n equal to 5. So therefore you have to select the sequence counter, the number of iteration, as 5, right? And the next initialization parameter is that flip-flop Qn plus 1 is also needs to be made 0. Once this initialization is done, you are supposed to compare Qn and Qn plus 1. Now you have to compare the values of Qn. Now what is this Qn? Qn is the least significant bit of QR register, right? Now these values Qn and Qn plus 1, either it will result into 1 0, this is Qn and Qn plus 1, or it can be 0 1, again Qn is this side and Qn plus 1 is this side, or it can result into both, either 0 0 or 1 1. Now what if Qn is 0 and Qn plus 1? We have to carry out one operation, that the content of accumulator register you have to add with the content of BR register and store that value into again accumulator. Now if it is Qn is 1 and Qn plus 1 is 0, then you are supposed to carry out an operation, accumulator content you are going to add with BR bar plus 1, right? So it is same as that of this. So accumulator content is added with 2's complement of BR. Okay, again save the results in AC, right? So if it is 0 0 or 1 1, then you should not do anything to the accumulator register. Now once this is done, so what is the next step is that we have to move arithmetic shift right the accumulator content, the along with the QR register and Qn plus 1. flip-flop. So accumulator, QR, Q1 plus 1, all the bits that are been involved in these three will be shifted right arithmetic, right? And remember that this is not a normal shift right, it is an arithmetic shift right. Arithmetic shift right means what? The empty bit is filled with the carry, not always 0. Okay, so if the sign bit is 0, then it will empty bit will be filled with 0. If the sign bit is 1, the empty bits are filled with 1. And uh, then what next we have to do? The sequence counter needs to be decremented by 1. The next sequence counter needs to be decremented by 1. If the sequence counter is not equal to 0, right? If the sequence counter is not equal to 0, then you are supposed to do what? You have to repeat this iteration. You have to repeat this iteration. If the sequence counter is equal to 0, then you have to stop, and the result will be available in accumulator and QR register. So QR register will contain the lower byte of the product, and accumulator will contain the higher byte of the product. So higher byte of the product is available in accumulator, and lower byte of products will be available in QR register. So this is all about the algorithm. Now we will take one example, and we are going to apply this Booth's algorithm, how actually the operations are being carried out in the hardware. I am going to perform the operation minus 15 multiplied by plus 30, right? So this could be you consider it as a multiplier, this as a multiplicand. So multiplicand will be in BR register and multiplier will be in QR register. Okay, so make a column. Now how many bits we require for that? Now right here. So minus 15. So what is minus 15? In which range it falls? N equal to 5. So right here the sequence counter value is 5. This is very important. If you fail to fix this sequence counter, then the rest of the steps that you follow in the Booth's algorithm iterations will go wrong, right? So sequence counter needs to be correctly fixed, that is 5. Now look at this algorithm that either accumulator content is added with BR, or the accumulator content is added with BR plus 1. So what I do, I will first find out the BR, and then I will have 1's complement plus 1. That value also I will find out. Now what is the value of BR? BR value is minus 15. Minus 15. Now you have to calculate, you need to represent this minus 15 in binary. So how many bits you have to take? First you have to write plus 15. Now how many bits you have to use? 5 bits. So I'm going to write 0, 1, 1, 1, 1. No doubt 15 can be fixed into 4 bits, but remember the sequence counter needs to be 5, not 4. So you have to remember this logic. So plus 15 you write it, and then you take 1's complement of this. 1's complement, it is 1, 4 zeros, and then you are going to add plus 1 for this, so that you will get the 2's complement. So finally you will get 2's complement, and the answer that what we got 2's complement is the negative of that positive number. So this will represent minus 15. So this, right? So now what is BR? BR is equal to 1, 0, 0, 0, 1, and this represent minus 15. That you have to remember. Now what is BR plus 1? So BR bar plus 1 we have to calculate. Now how to find out? So write the BR, take the complement of BR. So this is BR 1, 0, 0, 0, 1. Now what is BR bar? So just take the 1's complement of this, complement 1, 1, 1, 0, and then you are going to add 1 for this, and finally you will get 0, 1, 1, 1, 1, right? So what is BR bar plus 1? It is equivalent to 0, 1, 1, 1. So all these things you have to set aside. So this is BR, So just I will highlight this one so that for us it is easy to remember. Now our next step is that you have to create a table. This I will reserve for the accumulator. So I'm going to fix this as for accumulator, and remember the algorithm that it needs to be shifted accumulator, QR and n plus 1, right? So accumulator, this is, and this is our QR register, and this field is qn plus 1, and then this is sequence counter. And these two columns I have, and remember I have drawn five columns, 1 2 3 4 5, because of the sequence counter is 5. Okay, and this I will do it separately so that we cannot make any mistakes. Even it is available here qn plus 1, and this is qn. Okay, so the LSB of the QR is qn. So but to be very particular, I'm writing this qn and n plus 1 separately so that we can't make any mistake while the computation, while performing the iterations. Now what is the initial steps? The initial step is what? We have to make accumulator 0, BR as multiplicand, QR is multiplier. So BR is done. We have made the BR value, and BR bar plus 1 value is ready. Now what we are supposed to do is accumulator, you make it zeros, right? So initially it should be 0. And what is QR register? QR register is multiplier. So plus 13, and in 5 bits you are supposed to write. So QR is plus 13, right? In 5 bits you have to write. So this is 0, this is 8, this is 412, and this is 113. So this 0 1 1 0 1 is what? 13, and that is QR. And qn plus 1, initially it is 0, and the sequence counter is set to 5. Now qn is 1. Okay, qn is 1, and qn plus 1 is 0. Now if it is 1 0, look at the algorithm. If it 1 0, you have to add BR bar plus 1 to the accumulator. Accumulator content is already there. Now what is BR bar plus 1? So write it here, 0, then it is 1 1 1 1. Now perform the addition between these two, and you are going to get the answer as 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 1 and 0, right? So once we perform this operation, you have to do arithmetic shift right accumulator, QR and qn plus 1, right? So this 0 will come here, and this 1 will go here, that we are shifting towards right? And this 0 will come and reside here. This 1 will here, this 1 will be here, this 0 will be here, and this 1 will shift here. And this, the empty 1 that has been created, so whatever it was available here, this that needs to be put here. If it is 0, you fill it with 0. If it is 1, you fill it with 1, right? And the sequence counter is decremented by 1. Now the 5 will reduce to 4, right? So one iteration we have done. Now what next we have to supposed to do is, again, since it is not equal to 0, in the algorithm we have seen, if it is not equal to 0, you have to again look at the value of qn and n plus 1. Now what is qn is, again I select the a different pen over here. Now qn is 0, qn is 0, and qn plus 1 is 1. Now what happens if it is 0 1? So what we have to do, we have to add the content of BR with the accumulator. Now what is the content of BR? The content of BR is 1 0 0 1, right? And you have to perform the addition, right? So the addition between these two, the addition between these two. So 1 plus 1, 2. In binary, how we write 1 plus 1, 2. So it is like this, 0, 1. So 1, 0 is 2. So 1 plus 1, 2, right? So 1 plus 1, 2. And 0 plus 0 plus 1 is 1. 0 plus 1 is 1. And then again you have to perform the arithmetic shift right. So how we have done here, arithmetic shift right. So again we have to perform the arithmetic shift right. So this one will come over here, this one will come over here, and this 0 will come over here, this 0 will come over here, and this goes on. And the empty bit we need to shift here. Again, this empty bit you have to fill with the sign bit. So this is the sign bit, right? So 1 1. So 1 1 triple 0, and this 1 will come over here, 1 0 double 1 0, and the sequence counter is reduced to one more, 4 minus 1, it will become 3. Since it is non-zero, so again we have to repeat the iteration. And if it is now, what is the value of qn? So qn is 1, qn is 1, and qn plus 1 is 0. Okay, fine. Now if it is 1 0, so again you have to add br bar plus 1 to the accumulator. So what is this? Br bar plus 1. So 0 4 1. Again perform the addition. 0 plus 1. So what is 0 plus 1? 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 1 plus 1. You have to do the carry out the operation between the top row and the next, right? Don't include this one. So 1 plus 1 plus 1, 3. So 3 we will write in binary. 1 plus 1 is 2. And whatever the carry that has been resulted out needs to be ignored, discard. And what next? Again you have to perform the arithmetic shift right. So this 0 1 0 1 1, and this empty bit is again filled with, since it is 0, so it will be filled with 0. And this 0 1 0 double 1, and this will go off, and the counter again it is decremented by 2. Now since it is non-zero, we have to repeat this iteration, and this time the value of qn is 1, and qn plus 1 is also 1. And if you look at the algorithm, if qn and n plus 1 is either 1 1 or 0 0, nothing to do with the accumulator, directly you have to perform the arithmetic shift right. So I'm going to perform the arithmetic shift right directly here. So 0, this 0 will move here, right? And this empty bit created is filled with the sign bit, that is 0, and 0 0 1 0 1 1, right? 0 0 1 0 1 1 0 1 0, and this is 1. And again the sequence counter is reduced by 1. Now what next? Again, since it is not equal to 0, so again I need to repeat the iteration. Now this iteration, the value of qn is 0, and it is 1. Now if it is 0 1, so if it is 0 1, you have to add br to the accumulator content. Now what is br value? You just write it down. It is 1. It is br value 0. Br value is 1 0 0 0 1. Again perform the addition. You have to perform the addition between these two, right? So 0 plus 1, it is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. And next you have to perform the arithmetic shift right. So this 1 will go here. Again the empty bit will be filled with, replaced with the sign bit. 1 double 0. So 1 double 0 double 1, and this 1 1 0 1, and this 0, and this will discard, it will go off, and the counter will become finally sequence counter 0. Now here, this Since the sequence counter is 0, you have to stop the iteration and you got the final answer. And remember what I said you, that in the algorithm, your product will be available, higher byte will be available in accumulator, and your lower byte of your product will be available in QR register. So just extract what is your accumulator. It is 11001, right? And so your answer, I will just highlight this one. So this is your accumulator and this is your QR register. So up to here, don't take this 2 in the answer. So, and 11101. So this is your answer. So just we will verify whether you got this answer or not in the calculator. Just open the calculator and type. So you can go to the programmer and just type here 15, that is minus, multiplied by plus 13, that turns out to be minus 195. And what is the binary value? Binary value is 1. You can just look at here, 10111100, right? And all rest are 1 1. Since it is in it is in the quiet word 64-bit format, so not to worry. So just we will take the first 1 0 1 1 1 1 0 0 1 1, and this will be backside 1 1, whether it is the 32-bit format or 64-bit format, irrespective of that. So this is your final answer, that is 1 minus 195, that we have been verified with the calculator. Remember friends that in the examinations you can get both negative numbers. So either you will get minus 15 multiplied by minus 15, or you may get plus 7 multiplied by minus 3, right? Any combination. So we have done this part, minus 15 and plus 13, one minus and the other one plus, if both are minus minus, right? So this QR also you have to represent is 2 complement here, and for accumulator also, for what we have done for negative, again you have to use the 2's complement, and you need to follow the same steps. If both are positive, nothing to worry. So as it is, you can write it and you can perform accordingly. So if you have any questions, you can contact me uh, uh, through my mail ID. So thank you very much, or you can write the comment uh, in the comment box, and I will contact you if you have any further queries in the Booth's algorithm. Thank you very much. All the best.